Hello viewers, welcome to Sleepy Mind channel. Tonight we'll be exploring the edge of space. Imagine you are a pilot. You are pushing your throttle to its absolute limit, climbing higher than any commercial airliner dare venture. But as you look at your instruments, something terrifying happens. The controls go mushy. Your wings, which have held you safely in the sky for your entire career, stop gripping the air. There is no air. You are no longer flying. You are falling, but you are falling so fast that you miss the Earth entirely. Welcome to 100 kilometers above our heads. Welcome to the Kármán line. Most people think space begins where the air completely vanishes. But the truth is much stranger. The atmosphere doesn't just stop like a wall. It fades out like a ghost. Even hundreds of kilometers up, there are stray molecules of gas drifting in the vacuum. So, how do we decide where Earth ends and space begins? It isn't about where the air ends. It's about where the laws of aviation break down and give way to the laws of astrophysics. It is the exact boundary where a wing becomes completely useless and only a rocket engine can save you. To understand why this happens, we have to look at the physics of flight. An airplane stays in the sky because air flows over its wings, creating a pressure difference called lift. The higher you go, the thinner the air becomes. To maintain lift in thin air, you have to fly faster. In the 1950s, a brilliant Hungarian-American physicist named Theodor von Kármán sat down with a pen and paper to calculate the ultimate limit of flight. He asked a radical question. At what altitude would an airplane have to fly so fast to stay aloft that its speed would equal the speed required to orbit the Earth? The math yielded a startlingly clean answer, roughly 100 kilometers, or 62 miles, above sea level. At this precise altitude, if you want your wings to generate enough lift to hold you up, you have to travel at roughly 28,000 kilometers per hour. But here is the cosmic joke. If you are traveling that fast, you don't need wings at all. Centrifugal force takes over. You are in orbit. You have transitioned from an airplane to a satellite. Beyond this line, space belongs to no nation. It belongs to humanity. Inspired by the philosophy of Theodor von Kármán. Theodor von Kármán wasn't just a cold mathematician staring at equations. He was a man deeply fascinated by human ingenuity and terrified by human conflict. Living through both world wars, he watched aircraft evolve from fragile wooden canvas toys into terrifying weapons of mass destruction. When he calculated the Kármán line, he wasn't just solving a physics problem. He was trying to create a psychological sanctuary for mankind. He argued that while the airspace above a country belongs to that nation's military defense, the vacuum above 100 kilometers should be legally recognized as international territory. He envisioned it as a boundary where human squabbles, borders, and flags cease to matter. Think about the first astronauts who crossed this invisible threshold. When Yuri Gagarin or Alan Shepard looked down from just above the Kármán line, they didn't see the borders drawn on our maps. They didn't see passport control or political factions. They saw a terrifyingly fragile, bright blue marble wrapped in an atmospheric layer as thin as the skin of an onion, surrounded by a hostile, freezing infinity. When we cross the Kármán line, we leave behind our earthly identities. For the few minutes or days we spend above it, we are no longer citizens of a country. We are simply representatives of a fragile species looking back at its only home. If you were to step outside a spacecraft at the edge of the universe without a suit, you might think the cold would kill you first. Or perhaps the lack of oxygen would make you pass out. But physics has a much more violent fate in store for the unprotected human body. Long before you reach the Kármán line at just 19 kilometers up, you hit a biological wall. It is a point where the very fluid that keeps you alive turns against you. We are taught in school that water boils at 100 degrees Celsius, 212 degrees Fahrenheit. But that is only true if you are standing at sea level. wrapped in the heavy, protective blanket of Earth's atmospheric pressure. The air pressing down on us acts like an invisible lid on a pot, keeping liquid stable. As you climb higher into the stratosphere, the weight of the atmosphere drops drastically. The invisible lid lifts, and when you reach 19 kilometers, 63,000 feet, above the Earth, the atmospheric pressure drops to a mere 6% of what it is at sea level. At this pressure, the boiling point of water drops significantly. It drops so low, in fact, that it matches the exact internal temperature of the human body, 37 degrees Celsius, 98.6 degrees Fahrenheit. This terrifying threshold is known as the Armstrong limit. If an astronaut or a high-altitude pilot suffers a sudden cabin depressurization at this height, the consequences are immediate and horrifying. The moisture on your tongue, the tears in your eyes, and the fluid lining your lungs will literally begin to boil away into vapor. Contrary to Hollywood sci-fi movies, your blood inside your veins does not instantly boil throughout your entire body. Why? Because your circulatory system is a closed, pressurized loop. Your heart and blood vessels keep your blood under a slightly higher pressure than the outside environment. However, the fluids in your soft tissues, your muscle layers, and your respiratory tract will expand rapidly. Your body will begin to swell to twice its normal size as water turns to gas inside your flesh. You have roughly 9 to 11 seconds of conscious thought left before your brain is starved of oxygen. The Armstrong limit is named after Dr. Harry Armstrong, a visionary founder of U.S. Army aerospace medicine in the 1930s. Armstrong was a man obsessed with protecting pilots who were pushing their aircraft higher than ever before. He didn't just study these effects in a textbook. He built primitive vacuum chambers and stepped inside them himself, risking his own life to watch how low pressure affected living tissue. But the most profound human story of the Armstrong limit belongs to a man named Joe Kittinger. In 1960, as part of Project Excelsior, Kittinger rode a helium balloon up to an astronomical altitude of 102,800 feet, way past the Armstrong limit, and jumped out of it just to see if a human could survive a freefall from the edge of space. During his agonizingly slow ascent in an open gondola, the pressure seal on his right glove failed. As he crossed the Armstrong limit, his right hand was exposed to the near vacuum of space. He knew that if he told Mission Control, they would cancel the flight and order him to come down, ruining years of scientific research. So Joe Kittinger chose to say nothing. He endured agonizing pain as his right hand swelled to twice its normal size, the fluids in his knuckles and skin vaporizing under the low pressure, turning his hand into a useless, agonizingly stiff block of flesh. He kept his eyes fixed on the black sky above and the thin blue line below, trusting the heavy pressure suit protecting the rest of his body. He completed the jump, falling through the stratosphere at near the speed of sound, and survived. His hand eventually returned to normal once he re-entered the heavy air of Earth. Kittinger's swollen hand serves as a stark, human reminder. Earth's atmosphere is not just air we breathe. It is a pressurized suit that keeps our very bodies from unraveling. When night falls on Earth, the clouds we know, the heavy rain clouds, the fluffy summer cumulus, turn gray, then dark, and finally vanish into the shadows of the evening. But if you travel north, to the fringes of the Arctic Circle during the summer solstice, the dark sky hides a ghostly secret. 85 kilometers above the ground, right at the jagged lip of outer space, clouds are glowing in the dark. They are called noctilucent clouds, and they are built from the ashes of dying stars. The name noctilucent literally translates from Latin to night shining. To see them is to look at something that shouldn't logically exist. They are the highest clouds in Earth's atmosphere, forming in a zone called the mesosphere, a hyperfrigid graveyard where the Earth's air makes its final stand against the vacuum of space. Normal clouds form a few kilometers up, born from evaporated ocean water clinging to dust or sea salt. But at 85 kilometers up, the air is 100,000 times drier than the Sahara Desert. It is a near vacuum, yet somehow ice crystals manage to gather here in numbers so vast they can be seen from space. How does water find a home in a cosmic desert? The answer arrives from the depths of the solar system. To build a cloud, you need two ingredients, water vapor and a solid particle for that water to freeze onto, known as a nucleus. The water vapor gets to the mesosphere through a bizarre atmospheric elevator. During the summer, global wind patterns create a massive upwelling, pushing tiny amounts of moisture up into the upper atmosphere. As this air rises, it expands and cools drastically. Paradoxically, while the surface of the Earth is warm during the summer, the mesosphere becomes the coldest place on or around the planet, plunging to temperatures as low as -130 degrees Celsius, -202 degrees Fahrenheit. But the water vapor still needs something to cling to. There is no dust or pollution from cities that can float 85 kilometers high. Instead, the atmosphere relies on imports from deep space. Every single day, Earth is bombarded by roughly 100 tons of cosmic debris, meteors and micrometeorites tearing into our atmosphere at blazing speeds. As these space rocks burn up, they leave behind a microscopic trail of meteor smoke, fine particles of iron, magnesium, and silicon drifting in the upper air. When the rising water vapor hits the freezing mesosphere, it finds these tiny grains of alien dust. The water freezes instantly around the meteor smoke, creating ice crystals no larger than the wavelength of visible light. Because they are so high, even though the ground below is in darkness, these clouds are still catching the rays of the sun curving around the edge of the Earth. They act like a mirror, reflecting sunlight down to the dark side of the planet. It felt as though the natural order of the world had shifted. The sky was weeping light. From an anonymous journal entry, London, 1883. Human beings did not always see noctilucent clouds. In fact, throughout thousands of years of recorded human history, there is not a single mention of them. No ancient Greek philosopher, no medieval astronomer, and no indigenous storyteller ever wrote about electric blue webs in the midnight sky. That all changed in the summer of 1883. On an island in Indonesia, a volcanic mountain named Krakatoa violently exploded. It was one of the most catastrophic volcanic events in modern history, blowing the island apart with the force of 200 megatons of TNT. The sound wave traveled around the globe 4 times. The explosion blasted millions of tons of ash, sulfur dioxide, and water vapor clean out of the lower atmosphere, punching a hole straight into the stratosphere and mesosphere. A few weeks later, people in London, Berlin, and Moscow stepped out of their homes at midnight and gasped. The sky was alive with an eerie, unnatural, glowing blue luminescence. Scientists like T.W. Backhouse in England wrote down the first frantic descriptions of these night-shining clouds. People were terrified. Many believed the atmosphere had been permanently damaged, or that the world was ending. Over time, the volcanic ash from Krakatoa settled, but the noctilucent clouds didn't vanish. In fact, over the last few decades, they have been getting brighter, and they are moving. Once confined strictly to the poles, they are now being seen as far south as Colorado, Italy, and Japan. Why? Because humans have changed the chemistry of the atmosphere. As we release more methane into the air, those molecules drift upward. When methane reacts with oxygen in the upper atmosphere, it breaks down into water vapor. By burning fossil fuels and raising cattle on the ground, we are inadvertently feeding water to the edge of space. Today, when an amateur astronomer stands in a dark field, looking up at that brilliant blue glow, they are witnessing a beautiful, melancholic hybrid of two worlds. They are looking at water vapor created by human industry on Earth, frozen solid around the ash of a shooting star that traveled across the galaxy for billions of years, just to meet at the edge of our world. We like to think of space as an empty void, a quiet neighbor living just above our heads. But if human eyes could see electricity, the sky above would look like a raging, glowing ocean of fire. Between 60 and 1,000 kilometers high lies a frantic, hypercharged realm called the ionosphere. Without it, life on Earth would be sterilized by solar radiation, and humanity would have remained isolated, unable to speak across oceans. In the late 1800s, the greatest scientific minds in the world agreed on a fundamental rule of the universe. Wireless communication over long distances was impossible. Radio waves travel in straight lines, just like light. The Earth, however, is a curved sphere. If you stood on the coast of England and tried to beam a radio message across the Atlantic Ocean to North America, the signal would simply shoot off the edge of the horizon and vanish forever into the depths of space. The curve of the ocean would act like a massive hill blocking the signal. But in December of 1901, a stubborn Italian inventor refused to listen to the math. He built a massive transmitter, set up a receiver 3,500 kilometers away, and waited. What he didn't know was that the edge of space was about to act as a giant, cosmic mirror, bouncing his voice back down to Earth. The ionosphere exists because our atmosphere is constantly at war with the sun. The sun pours out an endless torrent of high-energy X-rays and ultraviolet radiation. When these powerful rays slam into the thin gases at the edge of our atmosphere, they don't just warm the air, they destroy it. The radiation hits atoms of nitrogen and oxygen with such immense violence that it knocks the electrons clean out of their orbits. This process is called ionization. What is left behind is a highly volatile, fluid layer of plasma, a sea of free-floating negative electrons and positive ions. This electrified layer is divided into three sublayers, the D, E, and F layers, each shifting in density between day and night. Because this layer is packed with free electrons, it behaves exactly like a giant sheet of metal suspended in the sky. When a low-frequency radio wave from the ground hits this sea of electrons, it causes them to vibrate. Instead of passing through into space, the radio wave is gathered up by the plasma and hurled back down toward the ground. This is known as skywave propagation. The signal zigzags between the surface of the Earth and the ionosphere, hopping around the curvature of the globe like a rock skipping across water. The man who defied the laws of physics was Guglielmo Marconi. Marconi was not a theoretical physicist. He was a practical dreamer. When he announced his plan to send a wireless signal across the Atlantic Ocean, the scientific community openly mocked him. The famous mathematician Henri Poincaré argued that the signal would simply leak into space. Investors backed out, calling Marconi a fraud. Undeterred, Marconi poured his own wealth into the project. He constructed a massive array of aerial wires suspended by giant masts in Poldhu, Cornwall, on the southwest tip of England. Then he sailed across the stormy Atlantic to St. John's, Newfoundland, Canada. He set up his receiving station on Signal Hill, using a kite flying 150 meters in the air to hold up his receiving antenna. On December 12, 1901, the weather was atrocious. The wind tore at his kite, threatening to snap the wires. Marconi sat in a cold, stone room, pressing a single earphone to his head, straining to hear over the roaring Atlantic wind outside. He had instructed his team in England to transmit the letter S in Morse code, 3 simple, short clicks, at exactly midday. At 12:30 p.m., through the chaotic hiss of atmospheric static, Marconi heard it. Click, click, click. He handed the earphone to his assistant, George Kemp, and asked, "Can you hear anything?" Kemp confirmed it. The 3 faint clicks had traveled from England, shot up into the sky, bounced off the invisible electrical ocean of the ionosphere, and shot back down into a rainy room in Canada. Marconi had no idea why it worked. He didn't know the ionosphere existed. He simply proved that the sky could hold a message. The ionosphere is a living reminder that the edge of space isn't just a boundary where human life ends. It is a functional mechanism that makes modern human society possible. Every time you see the northern lights dancing across the poles, or listen to an emergency broadcast over an AM radio station in a remote corner of the planet, you are witnessing the sun and the earth dancing together at the threshold of the cosmos, holding up a mirror so humanity can talk to itself. If you were to read the weather report for the upper edge of space, you would be forgiven for thinking you were entering the gates of hell. At an altitude of 300 kilometers, inside a layer called the thermosphere, the air temperature climbs to a staggering 2,500 degrees Celsius. That is hot enough to melt steel, liquefy titanium, and turn glass into running water. Yet, if you stood out there in a standard t-shirt, you wouldn't burn. You would instantly freeze to death. To our earthbound brains, this sounds like a logical impossibility. How can something be thousands of degrees hot, yet completely freezing at the exact same time? The answer lies in a cosmic optical illusion, a fundamental misunderstanding of what temperature actually means. We live our lives at the bottom of a heavy atmospheric ocean, where we confuse the concepts of temperature and heat. At the edge of space, physics strips away this luxury, exposing a mind-bending reality where an object can be engulfed in a roaring, atomic furnace and still remain trapped in a deep, icy freeze. To unpack this paradox, we have to look at how molecules behave. Temperature is not a measure of how warm something feels to human skin. Scientifically, temperature is simply a measure of kinetic energy, how fast the atoms in a gas are moving around. In the thermosphere, the air is incredibly close to the sun's direct fury. It absorbs massive amounts of high-energy X-rays and ultraviolet radiation. This raw energy slams into the few, scattered air molecules left at this altitude, causing them to vibrate and fly around at astronomical speeds, climbing up to several kilometers per second. Because those molecules are moving so incredibly fast, their kinetic temperature is mathematically calculated to be up to 2,500 degrees Celsius, 4,532 degrees Fahrenheit. But here is the catch. The air in the thermosphere is a near vacuum. It is so thin that a single molecule might travel for several kilometers before it accidentally bumps into another one. If you were to step outside into this layer, heat requires matter to travel. Because the air molecules are so incredibly far apart, almost none of them would actually touch your skin or your spacecraft. The roaring 2,500 degrees Celsius temperature has no way to transfer its energy to you. Instead, the dominant thermal force acting on your body would be radiation. You would be radiating your own body heat out into the empty, freezing sink of the universe. The vacuum would steal your warmth instantly, ignoring the hyper-fast, superheated molecules zipping harmlessly around you. My visor was completely iced over. I was blind, drowning in my own sweat, and frozen to the core all at once. Adapted from the logs of astronaut Gene Cernan, Gemini 9A. No human being experienced the terrifying reality of this thermal illusion more brutally than NASA astronaut Gene Cernan during the Gemini 9A mission in 1966. Cernan stepped out of his tiny spacecraft into the thermosphere for what was supposed to be a routine spacewalk. But NASA was still in its infancy, and they did not yet understand the brutal engineering challenges of working in a thermal vacuum. The moment Cernan entered the void, he was caught in a nightmarish tug-of-war between cosmic extremes. The side of his suit facing the sun was bombarded by raw radiation, heating up to over 100 degrees Celsius. But the side facing away from the sun, looking into the deep shadow of space, dropped to a staggering minus 100 degrees Celsius. Because there was no dense air to distribute the temperature evenly around him, his suit had to fight two completely different universes at the exact same time. As Cernan struggled to move his stiff, pressurized suit, his body began to overheat from the immense physical exertion. He began sweating profusely, but because his spacesuit's cooling system was overwhelmed by the extreme environmental deltas of the thermosphere, the moisture from his breath and sweat had nowhere to go. The water vapor drifted to the inside of his helmet visor, which was facing the cold shadow of space. Instantly, the sweat froze solid onto the glass. Deep within a layer of space that scientists classified as thousands of degrees hot, Gene Cernan was completely blinded by a thick layer of ice growing inside his helmet. His heart rate soared to 180 beats per minute. He couldn't see his hands, he couldn't feel his fingers, and he was losing body heat to the dark void while his back was being baked by the sun. Using sheer human grit and blind intuition, Cernan managed to grope his way back to the hatch and pull himself inside the capsule, saving his own life. His ordeal forced space agencies to completely redesign spacesuits, inventing liquid cooling garments that artificially create a mini-Earth atmosphere inside the suit. Cernan's frozen visor stands as a monument to human vulnerability. At the edge of space, the numbers on a scientist's chart mean nothing. The universe will gladly freeze you solid inside an oven of invisible fire. When we look up at a clear night sky, it looks peaceful. It looks like an open road leading to the stars. But this peace is a lie. Surrounding our world is an invisible, radioactive minefield so lethal that it kept humanity pinned to its home planet for generations. They are the Van Allen radiation belts, a magnetic prison packed with millions of high-energy particles capable of ripping through human DNA like subatomic bullets. In 1958, the United States launched its very first successful satellite, Explorer 1, into orbit. It was a small, pencil-shaped device designed to carry out basic science experiments in the unknown territory beyond the atmosphere. On board was a small, rugged device built by a physicist named James Van Allen, a Geiger counter meant to measure the harmless cosmic rays drifting through space. As the satellite climbed higher, crossing into the upper atmosphere, the Geiger counter behaved exactly as expected, clicking rhythmically as it detected a few stray particles. But as the satellite reached an altitude of roughly 1,000 kilometers, the radio telemetry coming back to Earth suddenly went haywire. The Geiger counter didn't just speed up, fell completely, deathly silent. At first, the team on the ground thought the instrument had broken. But James Van Allen realized something far more chilling. The instrument wasn't broken. It had been completely blinded. It had hit a wall of radiation so incredibly dense that the sensor was overwhelmed, paralyzed by an invisible ocean of electricity. To understand where this radiation comes from, we have to look deep beneath our feet. At the center of the Earth sits a spinning, churning core of liquid iron. This motion turns our planet into a giant bar magnet, projecting a massive magnetic shield called the magnetosphere out into space. Meanwhile, the sun is constantly throwing out the solar wind, a high-velocity river of highly charged electrons and protons traveling at millions of miles per hour. When this deadly solar wind slams into Earth's magnetic shield, it doesn't always bounce off. Instead, the magnetic field lines act like a giant cosmic fishing net. They catch the high-energy particles and trap them, forcing them to spiral frantically back and forth along the magnetic lines wrapping around our planet. This creates two distinct zones of terror. The inner belt, stretching from 1,000 to 6,000 kilometers up, packed with high-energy protons blasted from deep cosmic rays. This is the most dangerous zone. The particles here carry enough energy to penetrate thick aluminum shielding. The outer belt, stretching from 13,000 to 60,000 kilometers high, comprised mostly of energetic electrons captured from the solar wind. If a human being were to sit inside the heart of the inner Van Allen belt without massive, heavy lead shielding, they would receive a lethal dose of radiation within a matter of days. The particles would collide with the water molecules in their body, creating free radicals that would dismantle their cellular structure from the inside out. We knew the risks, we knew the numbers, but you can't reach the moon if you are too afraid to run through the fire. Reflections on the Apollo navigation design. For a decade after their discovery, the Van Allen belts loomed over the scientific community like an insurmountable wall. Scientists openly wondered if human spaceflight was a dead end. How could we ever send humans to the moon, Mars, or beyond if they had to cross through a radioactive gauntlet that could kill them before they even left Earth's backyard? When NASA launched the Apollo program in the 1960s, they knew they couldn't engineering a spacecraft heavy enough to block the radiation. Standard lead lining would make the Saturn V rocket too heavy to lift off the ground. So, the engineers at NASA didn't try to outshield the radiation. They decided to outrun it. When Apollo 11 launched in July 1969, Neil Armstrong, Buzz Aldrin, and Michael Collins weren't just flying to the moon. They were playing a high-stakes game of cosmic dodgeball. Trajectory experts designed an incredibly precise flight path called the translunar injection. Instead of flying through the thickest, deadliest heart of the inner belt, they aimed the spacecraft through the thinnest outer fringes of the radiation field. They fired their third-stage rocket engine, accelerating the spacecraft to a blinding speed of nearly 40,000 kilometers per hour. As the crew shot through the invisible belts, they couldn't see the danger. They couldn't smell it or taste it, but it was there. Inside the cabin, cosmic rays occasionally sliced straight through the metal hull of the spacecraft and passed through the astronauts' skulls. When these particles hit the retinas of their closed eyes, the astronauts reported seeing eerie, ghostly flashes of white light inside their own brains, a phenomenon known as cosmic ray visual phenomena. Because of their immense speed and carefully mapped trajectory, the Apollo 11 crew cleared the radioactive cage in less than 30 minutes. Their total radiation dose for the entire trip was less than what a person receives from a standard medical CT scan. The Van Allen belts are a poignant reminder of our place in the cosmos. They are a double-edged sword. They act as a protective womb that guards life on Earth from being incinerated by the sun, but they also serve as a strict, celestial boundary marker. They tell us that space is not a playground. It is an unforgiving frontier that demands our absolute best engineering, our highest intelligence, and an audacious amount of human courage just to cross the front porch. For centuries, humanity has stared at the moon and seen it as a distant, lonely wanderer floating in the harsh vacuum of deep space. We drew a line in our minds. Here is Earth, there is the sky, and out there is the cold, empty universe. But the universe does not care for our human boundaries. In the twilight of the space race, we discovered an astonishing cosmic truth. The atmosphere of Earth does not end at 100 kilometers. It does not end at 1,000 kilometers. It stretches out so far into the dark that the moon itself spends its entire life flying inside the warm, protective embrace of our planet. When astronauts left for the moon in 1969, they believed they were leaving Earth completely behind. They thought they were crossing a sterile, black ocean between two distinct worlds. But space is a master of nuance. In the outermost layer of the edge of space, a region known as the exosphere, the rules of what constitutes an atmosphere become beautifully blurred. Here, Earth holds onto a massive, invisible halo of hydrogen gas known as the geocorona. It is a cloud so vast, so incredibly expansive, that it reaches a staggering 630,000 kilometers into space. That is almost twice the distance from the Earth to the moon. It means that every flag planted by Neil Armstrong, every crater on the lunar surface, and every piece of space hardware we have ever hurled into lunar orbit is technically sitting inside the final gossamer layers of Earth's air. How can an atmosphere exist so far out without being blown away by the solar wind? The exosphere is the ultimate cosmic borderland. Down on the surface, gravity holds heavy molecules like nitrogen and oxygen tight against the crust. But lightweight elements, specifically hydrogen, are unruly. They are born from water vapor breaking down in the lower atmosphere and slowly drifting upward over millennia. Once these hydrogen atoms reach the exosphere, they are incredibly far apart. A single cubic centimeter of space at this distance might contain just a few hundred atoms. By earthly standards, this is a vacuum cleaner's dream, far emptier than any vacuum we can create in a laboratory. However, because these atoms are still gravitationally bound to the Earth, they form a structured shell. When the unfiltered sunlight of deep space hits these stray hydrogen atoms, it excites them. The atoms absorb the sun's ultraviolet light and re-radiate it in a specific wavelength known to physicists as Lyman alpha radiation. To the naked human eye, the geocorona is completely invisible. It is a phantom, but to a telescope calibrated to see ultraviolet light, the Earth looks like it is wearing a magnificent, glowing shroud that bleeds gently into the blackness of the solar system. We didn't go to the moon just to look at the rocks. We went to look back at ourselves from a place of absolute clarity. Reflections on the Apollo 16 lunar surface experiments. The story of how we discovered the true scale of our home's embrace belongs to the crew of Apollo 16 in April 1972. While history loudly remembers Neil Armstrong's small step, it often forgets the profound scientific poetry accomplished by astronauts like John Young and Charlie Duke. Tucked inside their lunar module was a strange, gold-plated device that looked like a cross between a movie camera and a miniature cannon. It was the Far Ultraviolet Camera/Spectrograph, designed by a brilliant, soft-spoken African-American scientist named Dr. George Carruthers. Carruthers had spent his life engineering ways to see the invisible. He knew that Earth's heavy atmosphere blocked ultraviolet light from reaching ground-based telescopes, a feature that protects humans from skin cancer but blinds astronomers to the secrets of the cosmos. To get a clear picture of the universe, Carruthers needed to put a camera outside of Earth's heavy blanket. John Young set up the gold-plated camera in the stark, blinding dust of the Descartes Highlands on the moon. He pointed it back at the Earth hanging in the black lunar sky. When the film was brought back to Earth and developed, scientists gasped. The images didn't show a sharp, distinct blue marble floating in emptiness. They showed the Earth surrounded by an immense, spectacular, roaring cloud of ultraviolet light that billowed outward like a solar storm. For the first time, humanity saw that our home was much larger than the continents and the oceans we inhabit. Dr. Carruthers' camera proved that Earth is not a closed system. When you look up at the moon tonight, realize that you are looking at a celestial body that is not truly foreign. It is dancing inside our garden. We are bound to our satellite by a thread of ancient hydrogen, a ghostly reminder that the edge of space is not a wall that isolates us, but an extended embrace that connects our world to the rest of the cosmos. Every single day, our planet is fighting a silent cosmic war. The solar system is a shooting gallery, packed with millions of stray rocks, debris from dead comets, and jagged asteroids traveling fast enough to wipe out entire cities. They scream toward us at speeds that make a sniper bullet look like a crawling snail. Yet, you walk down the street without a helmet. You sleep soundly under a glass roof. Why? Because 80 kilometers above your head, the edge of space acts like an invisible, bulletproof vest. Ask almost anyone why shooting stars light up in the night sky, and they will give you the same answer: friction. They imagine the space rock rubbing against the air molecules like a hand rubbing against sandpaper, heating up until it ignites. But the science of the edge of space is far more counterintuitive. At 80 kilometers up in the cold heart of the mesosphere, the air is too thin to create that kind of friction. There simply aren't enough molecules to rub against the rock. The blinding light of a meteor isn't caused by friction at all. It is caused by something far more violent, the physics of pure, brutal compression. When a meteor hits the upper atmosphere, it is traveling at hypervelocity, anywhere between 11 to 72 kilometers per second, up to 250,000 kilometers per hour. At that speed, the air molecules directly in front of the rock simply cannot move out of the way fast enough. The meteor acts like an unstoppable piston slamming into a sealed cylinder. The air becomes violently trapped, compressed into an ultra-dense pocket of gas directly ahead of the leading edge of the rock. This is known as ram pressure. According to the fundamental laws of thermodynamics, when you compress a gas rapidly, its temperature skyrockets. The air in front of the meteor is compressed so violently that its temperature explodes to over 3,000 degrees Celsius, 5,400 degrees Fahrenheit in a fraction of a millisecond. The meteor isn't burning from friction. It is being shoved into a hyper-compressed furnace of its own making. This intense heat turns the air into a glowing envelope of superheated plasma. The intense thermal energy melts the outer layer of the rock, a process called ablation. The liquid rock is instantly stripped away by the oncoming air, exposing fresh layers to the furnace until the entire asteroid is literally vaporized into microscopic dust. I didn't think about space. I just thought the heater had exploded. And Hodges, recalling the afternoon of November 30th, 1954, the thinness of the line between cosmic protection and violent reality is perfectly captured by the life of a woman named Ann Hodges from Sylacauga, Alabama. On a chilly afternoon in November 1954, 31-year-old Ann was enjoying a quiet, mundane day. She was napping on her living room couch, wrapped in a thick quilts, while her mother knitted in the next room. High above Alabama, a 4.5 billion-year-old chunk of space rock was screaming through the mesosphere. The kinetic shield of the atmosphere did its job, compressing the air and tearing the asteroid apart, melting away 99% of its mass. But one small, stubborn fragment, an 8.5-pound piece of dense, black stone, survived the gauntlet. It dropped through the stratosphere, slowed down by the heavy air, and fell toward the town of Sylacauga. With a deafening crash, the space rock punched a hole straight through the roof of Ann Hodges' house. It bounced off a large, wooden console radio sitting in the corner of the room, ricocheted into the air, and slammed directly into Ann's hip while she lay on the couch, and woke up in an explosion of dust and smoke, screaming in agony. She looked down to find a massive, deep purple bruise the size of a dinner plate across her thigh. She had just become the only human being in recorded history to be directly struck by a meteorite. The aftermath of the event was a tragedy of human nature, and went from a private, quiet housewife to a global celebrity overnight. The police confiscated the rock. Her landlord sued to keep it. Public legal battles dragged on for years, ruining her mental health and fracturing her marriage. She eventually donated the rock to a museum and died in obscurity at a young age. But Ann Hodges' bruise remains a profound symbol. Every time you see a gentle, romantic shooting star streak across the night sky, remember what you are actually witnessing. You are watching the edge of space use the simple laws of physics to crush a cosmic assassin into dust. We live our lives beneath a shield of hyper-compressed air, a violent, beautiful wall of fire that stands between our fragile lives and the chaotic fury of the universe. We grow up believing that Earth is a permanent sanctuary, a perfectly sealed glass jar holding onto everything we need to survive. We think our gravity is an inescapable lock, but at the absolute edge of space, the jar is leaking. Every single day, every single hour, our planet is bleeding its own air into the vacuum of space, leaving an invisible, tragic trail of our atmosphere scattered across the solar system. If you could weigh the Earth on a cosmic scale, you would find it is on a diet. It is getting lighter. Every single year, our planet loses roughly 95,000 tons of gas to outer space. The edge of the atmosphere is not a solid roof. It is a porous, frayed borderland where the energetic particles of the sun are constantly stripping away our world's lifeblood. We are living on a world that is slowly evaporating. If this process carries on unchecked forever, Earth will meet the same grim fate as Mars, turning into a dead, dry, frozen desert stripped bare by the cosmos. This slow death happens primarily in the exosphere through a process known as thermal escape or Jeans escape, named after the British physicist Sir James Jeans. Down on the surface, gravity easily holds onto heavy gases like nitrogen and oxygen. But lightweight elements like hydrogen and helium are chaotic. Because they are light, the ambient heat from the sun causes them to vibrate and zip around at incredible speeds. At the edge of space, where the air is incredibly thin, these light molecules don't hit each other very often. If a hydrogen atom absorbs a high-energy photon from the sun, it can instantly accelerate past Earth's escape velocity, roughly 2 kilometers per second. With nothing blocking its path, the atom shoots straight out into the void, escaping Earth's gravitational grip forever. Worse still, Earth undergoes hydrodynamic escape. The planet's magnetic field lines open up near the north and south poles. Here, solar radiation ionizes oxygen atoms, turning them into charged particles. The solar wind behaves like a giant cosmic vacuum cleaner, latching onto these ions and ripping them away from the poles in a massive stream called the polar wind. We discovered that Earth has a shadow made of our own breath. We are painting the solar system with the pieces of our sky. Reflections from the ESA cluster mission scientists. For decades, this planetary bleeding was just a math equation on a chalkboard. No one had ever truly seen it. That changed in the early 2000s when the European Space Agency launched the cluster mission. A fleet of 4 identical spacecraft flying in a tight formation through the upper reaches of Earth's magnetic shield. The scientists working on the project were looking for data on solar storms. Instead, they stumbled upon an incredibly beautiful, melancholic sight. As the spacecraft passed behind the dark side of the Earth, their instruments detected a colossal, teardrop-shaped plume of oxygen ions streaming away from the planet's nighttime side, extending tens of thousands of kilometers into deep space. They realized that the Earth is traveling through the galaxy like a lonely goddess wearing a magnificent, frayed gown woven from her own atmosphere. Every time you take a deep breath of fresh air, you are breathing molecules that may one day drift up to the edge of space, catch a solar breeze, and leave this world forever. The realization is profoundly grounding. Our atmosphere is not an infinite, indestructible resource. It is a fragile, finite gift. The air we breathe is a transient passenger on this rock, slowly slipping through our fingers into the infinite dark, demanding that we cherish the vibrant blue world we have before it quietly evaporates into the history of the cosmos. Right now, as you sit reading these words, billions of invisible bullets are tearing through your body. They pass through your roof, through your skull, and straight through your DNA at almost the speed of light. They do not come from Earth. They do not even come from our solar system. They are cosmic rays, the radioactive shrapnel of dying stars that exploded millions of years ago. And the edge of our space is the front line where our atmosphere takes the bullet for us. If you were to step outside into the vacuum of space without protection, the sun would not be your only enemy. The entire universe is shooting at you. Deep space is packed with galactic cosmic rays, GCRs. These aren't rays of light. They are the stripped, naked nuclei of heavy atoms, mostly pure protons, traveling with such immense kinetic energy that they defy the laws of imagination. A single cosmic ray particle can carry the same kinetic energy as a professional baseball pitched at 100 miles per hour, all packed into a particle smaller than a single atom. When these cosmic bullets hit the upper edge of our atmosphere, they don't hit a wall. They hit a minefield. The resulting explosions create a chaotic, radioactive rain that defines the environment of high-altitude flight. When a high-energy cosmic ray slams into an atmospheric gas molecule in the stratosphere, it triggers a process called spallation. The collision is so violent that it shatters the target nucleus into pieces. The original cosmic ray vanishes, but its immense energy is converted into a spectacular cascade of exotic, short-lived subatomic particles: pions, kaons, electrons, and muons. This event is called a secondary cosmic ray shower. Muons are the heavy cousins of electrons. They are incredibly unstable, designed by physics to exist for only 2.2 microseconds before decaying into nothingness. Yet, because they are traveling so fast, Einstein's laws of relativity take over. Time slows down for the muon, allowing it to survive long enough to rip through the lower atmosphere and reach the surface of the Earth. Every single minute, roughly 10,000 muons pass through your body. Our atmosphere acts like a massive, 10-meter thick lead shield, absorbing the dangerous primary radiation and softening the blow into a harmless, ghostly drizzle by the time it reaches the sidewalk. The results of my observations can best be explained by the assumption that radiation of very great penetrating power enters our atmosphere from above. Victor Hess, 1912. We only understand this cosmic crossfire because of an audacious, death-defying Austrian physicist named Victor Hess. In the early 1900s, scientists noticed that the air on Earth was naturally radioactive, but everyone assumed the radiation was coming from minerals inside the ground. They believed that if you climbed up a tall building or a mountain, the radiation would drop to zero. Victor Hess wasn't satisfied with mountains. He wanted to go to the edge of the world to find out the truth. On August 7, 1912, Hess did something insane. He climbed into a fragile, wicker basket attached to a massive hydrogen balloon named Bowman. He packed the basket with 3 heavily insulated electroscopes, devices used to measure radiation, and ordered the ground crew to cut the ropes. Hess ascended to a staggering altitude of 5,300 meters, over 17,000 feet, without any oxygen equipment. The air grew thin, his lips turned blue from hypoxia, and the temperature inside the open basket plunged to a freezing -10 degrees Celsius. He was drifting dangerously close to passing out and falling to his death. But as he stared at his instruments through frostbitten eyes, he noticed something impossible. The higher he climbed, the faster his radiation meter spun. At 5,000 feet, the radiation stopped dropping. By the time he reached 17,000 feet, the radiation levels were 4 times higher than they were on the ground. Hess realized that the Earth wasn't poisoning the sky. The sky was poisoning the Earth. He had discovered cosmic rays, a feat that would earn him the Nobel Prize in Physics in 1936. Victor Hess's freezing, hypoxic balloon ride transformed our understanding of our place in the universe. It proved that our blue sky is not an empty canvas. It is an active battleground. The edge of space is a protective umbrella shielding us from the ancient, radioactive shrapnel of dying stars. We survive on this planet because a thin, invisible layer of air stands between our fragile cells and the eternal, raging crossfire of the deep universe. In the cosmic hierarchy, size usually dictates power. We fear the massive asteroids, the world-ending comets, the titanic forces of nature. But at the edge of space, humanity has manufactured a completely new kind of monster. It is an invisible, swirling storm of artificial shrapnel where a stray bolt, a frozen drop of rocket coolant, or a fleck of dried paint carries the destructive kinetic energy of an artillery shell. We are rapidly building a cage around our own planet, and the door is snapping shut. If you were to step outside the International Space Station for a spacewalk, your greatest fear might be a failing oxygen line or a tear in your suit. But the space agencies tracking your mission are terrified of something much smaller. They are watching the radar screens for space junk. Right now, orbiting just above the atmosphere, there are over 30,000 objects larger than a softball, 1 million objects the size of a marble, and over 100 million particles smaller than a grain of salt. Because there is no air resistance at this altitude to slow things down, these objects never stop. They are locked in a perpetual hypervelocity race around the Earth. At these speeds, the traditional laws of physics scale up into a nightmare. A tiny piece of metal no larger than a pea doesn't just scratch a spaceship. It creates a kinetic explosion that can depressurize a module and kill an entire crew in seconds. When two objects collide at this speed, they don't just dent each other. The energy of the impact is so massive that both objects instantly liquefy or vaporize, shattering into a cloud of thousands of new, smaller, jagged projectiles. In 1978, a visionary NASA scientist named Donald J. Kessler looked at these numbers and predicted a terrifying tipping point known as the Kessler syndrome. Kessler argued that once the density of space debris in LEO reaches a certain threshold, a single collision will spark an uncontrollable chain reaction. One dead satellite will smash into another, creating a cloud of debris that will go on to destroy 10 more satellites, which will destroy 100 more. Eventually, the edge of space will become a self-perpetuating, raging river of flying metal, destroying every weather, GPS, and communication satellite we own, and making it completely impossible for any future rocket to leave Earth without being instantly shredded. I looked out the window and saw a crater in the multi-layered glass. It was a cold reminder that we are flying through a minefield of our own making. Reflections from Space Shuttle Commanders. The reality of Kessler's warning isn't science fiction. It is etched into the very windows of our spacecraft. During the STS-7 mission of the Space Shuttle Challenger in 1983, astronaut Sally Ride and her crew were orbiting high above the Earth. Midway through the mission, a loud, sharp ping echoed through the forward cabin. When the astronauts checked the heavy, triple-pane quartz windshield of the shuttle, they found a startling sight: a deep, circular impact crater nearly half a centimeter wide eaten directly into the outer glass layer. When the shuttle returned to Earth, NASA engineers analyzed the microscopic residue left inside the crater. They expected to find pieces of a meteor. Instead, they found traces of titanium oxide, aluminum, and carbon, the exact chemical signature of household paint. A tiny, microscopic flake of dried paint had peeled off an old, discarded Soviet or American rocket booster from the 1960s. It had been drifting for decades, a ghost of human progress. If that paint chip had been just a few millimeters larger, it would have punched straight through the triple-pane windshield, instantly vacuuming the air out of the cabin and killing Sally Ride and her crew. Today, the International Space Station has to fire its thrusters and perform debris avoidance maneuvers multiple times a year just to duck out of the way of tracking space junk. The Kessler syndrome is a profound human mirror. It shows us that our habit of polluting our environments isn't limited to our oceans and forests. We have brought our disposable, consumerist culture to the very gateway of the heavens. The edge of space is warning us. If we do not clean up our ancient celestial trash, the sky will transform from a horizon of hope into an impenetrable, spinning cage of metal boneyards, trapping humanity beneath the clouds forever. If you walk out into a deep forest or a vast desert on a moonless night, far away from city lights, you might think you are experiencing true darkness. You look up and see the black spaces between the stars. But you are being deceived. The sky above you is never black. The edge of space is constantly alive with a soft, ghostly radiance that has been burning since the birth of our planet. It is called airglow, and it is the soundless, chemical breath of a world that refuses to go dark. For centuries, astronomers were baffled by a persistent optical problem. No matter how clean their lenses were, and no matter how remote their mountain observatories stood, their night sky photographs always suffered from a faint, strange background haze. At first, they blamed starlight scattered by space dust or light pollution from distant towns. But in 1901, the Swedish physicist and Nobel laureate Svante Arrhenius realized that the light wasn't coming from deep space, nor was it coming from human cities. The light was coming from the air itself. Airglow is a natural, global phenomenon where the upper mesosphere and lower thermosphere emit a constant, low-intensity light. It is so powerful that if you were to look at Earth from a deep space telescope, our planet would look like it is wrapped inside a glowing, translucent green bubble wrap, shielding us from the dark. Airglow is born from a beautiful chemical process called chemiluminescence, the exact same science that makes a plastic glow stick light up when you snap it. During the daytime, the upper atmosphere is violently bombarded by brutal ultraviolet light from the sun. This high-energy radiation slams into molecules of oxygen \BMO_2 and nitrogen, tearing them apart into single, lonely atoms of oxygen \BMO. The atmosphere essentially acts like a giant solar battery, storing up this raw cosmic energy within its broken chemical bonds all day long. When night falls and the sun sets, the solar energy source cuts off. The atmosphere begins to cool down, and those lonely, single oxygen atoms begin to seek each other out to reform stable molecules. As these atoms collide and fuse back together, a process called recombination, they cannot hold onto the excess energy they absorbed during the day. To stabilize, they must dump that energy. They release it in the form of a single particle of light, a photon. Because of the specific electron configurations of oxygen atoms at an altitude of 90 to 100 kilometers, this light is emitted in a stunningly precise wavelength of 557.7 nanometers, which human eyes perceive as a vivid, ghostly neon green. Higher up, around 250 kilometers, hydroxyl radicals and nitrogen atoms undergo a similar process, releasing a deeper, fainter red glow. I felt like I was looking at the heartbeat of the living world. It wasn't an empty planet. It was an illuminated soul. Reflections on the overview effect from ISS crews. While scientists can measure airglow with spectrometers, its true impact is psychological, experienced exclusively by the few human beings who leave the heavy air of Earth to look back from above. When astronauts arrive at the International Space Station, many of them suffer from an unsettling psychological condition known as cosmic vertigo. When they look out into the deep void during the orbital night, the blackness of the universe can feel crushing, hostile, and completely indifferent to human existence. It makes the astronauts feel terrifyingly insignificant. But then, their eyes adjust to the darkness, and they see the airglow. Astronauts like Ron Garan have written deeply moving accounts of seeing this phenomenon. They describe floating in a pitch-black cabin, looking down at a dark planet, and watching this luminous green thread perfectly tracing every continent, every ocean, and every boundary of the world. The airglow transforms the perspective of the observer. It makes the atmosphere look like a living, breathing skin. It provides a visual boundary that says, "Here is our home." Within this glowing neon wrapper, everything we love, every memory we have made, and every life that has ever existed is cradled in warmth. Airglow is a poetic reminder of the resilience of our world at the edge of space. It tells us that even when the sun goes down, and even when we find ourselves facing the cold, terrifying dark of an indifferent universe, our atmosphere continues to hold onto the light of the day, whispering across the cosmos that Earth is alive, and it is burning bright. If you could float at the edge of space, far above the clouds, you would expect to experience a state of absolute, serene silence. You are far away from the screaming traffic of cities, the howling of ocean winds, and the chatter of humanity. But if you were to look at the data from specialized acoustic sensors, you would realize that the edge of our world is actually deafening. It is trapped inside a permanent, haunting symphony of ultra-low frequency sound waves, a ghostly chorus of voices running around the globe that human ears can never hear. We are taught that space is a vacuum, and because sound requires a medium like air to travel through, space must be silent. While that is true for deep space, the boundary layer of our upper atmosphere tells a completely different acoustic story. Between 20 and 50 kilometers up, the air is thin, but it isn't empty. This region acts like an acoustic trap, gathering up the deepest, most powerful sounds generated across the surface of the entire planet and locking them into a continuous loop. These sounds are called infrasound, acoustic waves that vibrate at frequencies below 20 hertz, far below the threshold of human hearing. Even though you cannot hear them, these giant waves of compressed air carry enough raw kinetic energy to travel around the entire planet multiple times without ever losing their strength. To understand how the edge of space becomes a planetary microphone, we have to look at how sound behaves across different temperatures. Sound waves travel faster through warm air than they do through cold air. When a violent event happens on Earth, like an exploding volcano in Indonesia, a massive lightning strike in Africa, or an ocean storm in the Atlantic, it releases a massive pulse of infrasound. These long, lazy waves, stretching up to several miles from crest to crest, ripple upward into the sky. As they climb into the stratosphere, they hit a strange thermal layer. Thanks to the ozone layer absorbing ultraviolet light, the mid-stratosphere is significantly warmer than the layers directly above and below it. This sudden temperature change creates a phenomenon known as an acoustic duct. When the upward-moving infrasound waves hit this boundary, the temperature difference acts like a mirror, bending the sound waves and trapping them inside a narrow atmospheric hallway. The sound cannot escape into space, and it cannot easily fall back down to the ground. Instead, it bounces back and forth inside the edge of space, traveling across continents at the speed of sound, turning the upper atmosphere into a giant acoustic archive of everything happening on the planet below. We heard things up there that we couldn't explain. Deep, rhythmic thrumming sounds that felt completely alien. Dr. Daniel Bowman, stratospheric acoustician. For decades, the soundscapes of the edge of space were completely hidden from human science. We had sent astronauts and satellites through this zone, but we had never bothered to listen. That changed in the 2010s and 2020s when a dedicated, adventurous scientist named Dr. Daniel Bowman began launching custom-built infrasound microphones into the stratosphere using high-altitude helium balloons. Bowman's experiments were deceptively simple. He took small, specialized microbarometers, packed them inside insulated boxes, and attached them to giant latex balloons that climbed up into the near vacuum of space, 3 times higher than commercial jetliners can fly. When the balloons popped and the instruments parachuted back to Earth, Bowman downloaded the data and sped up the acoustic tracks by 1,000 times so they could be brought into the range of human hearing. What he heard was deeply unsettling. Through the headphones, the edge of space sounded like a haunted, dark industrial factory. There were deep, mournful groans, sharp metallic snaps, and a persistent, rhythmic low-frequency throbbing. Bowman and his team were able to identify some of the sources. They were listening to the sound of massive ocean waves crashing against the coast of Alaska from thousands of miles away. They were hearing the deep rumble of wind blowing over the peak of the Andes Mountains and the crackle of distant thunder in the tropics. But alongside the identifiable sounds, there were anomalies, mysterious, ultra-low frequency hums occurring in the dead of night that had no clear origin point on Earth. These recordings reveal a beautiful, haunting reality. The edge of space is not an empty, silent tomb. It is a living ledger of our world's violent vitality. It is a place where the collective voice of the earth, its storms, its mountains, its oceans, and its tectonic shifts, gathers together to sing a deep, permanent song that blankets the planet. A symphony of a restless world echoing along the threshold of the cosmos.